In the 10 years since LIGO first detected a gravitational wave, we have improved our detectors so that several times each week, LIGO sees waves from colliding black holes. To achieve several per week, we use radically new squeezed vacuum technology, which is also called squeezed light. In this talk, I will describe in greatly simplified form how we conceived and perfected squeezed vacuum technology. It was a 50-year struggle, mostly in American universities with government funding, and in year 44, it began triggering spin-off into private industry. I'll conclude with comments on the danger that political turmoil in America may be destroying this university-based route for creating new technologies. In 1972 and 73, 3 foundations were laid for squeezed vacuum technology. The first foundation was when Rainer Weiss at MIT invented the gravity wave detectors that we ultimately would build for LIGO. In this simplified model, 2 mirrors hang from overhead supports at the ends of perpendicular arms. A laser beam shown in red monitors the difference in arm lengths by interferometry. A gravitational wave stretches and squeezes the arms oppositely, so the mirrors move in and out, and due to interference of the light, the output signal light brightens and dims. The second was that upon learning of Weiss's invention, Vladimir Brzezinski in Moscow warned us that the gravitational waves might be hidden by the mirror's quantum fluctuations, a tiny shaking, a billion times smaller than an atom that can never be stopped. To conquer this mirror shaking, Brzezinski said that we must create some sort of quantum technology. Third, the key to that technology, vacuum fluctuations, was laid by another Russian, Yakov Zeldovich. Imagine a box filled with nothing, only a vacuum remains. The vacuum is filled with tiny fluctuations of everything that ever could reside inside the box, vacuum fluctuations. Zeldovich speculated, and he was probably right, that the Big Bang explosion that created our universe produced only vacuum fluctuations and nothing more. But those fluctuations, by feeding off the energy of the universe's expanding space, transformed themselves into all the matter that fills our universe today. Now, these 3 foundations were followed by a decade of frustrating gestation. From 1973 to 1981, Brzezinski and I and our students struggled to invent a quantum technology that protects the gravity wave signal from the mirror's quantum shaking. We found nothing very promising until one day in 1981, my student Carlton Caves had a brilliant insight. Vacuum fluctuations of light entering the interferometer backwards can control the mirror's shaking, Caves realized. In technical language, the vacuum fluctuations, by beating against the laser light, create fluctuating light pressure that controls the mirror's quantum state. Perhaps, Caves speculated, just as the Big Bang manipulates vacuum fluctuations to create all our universe's matter, similarly, we humans can manipulate vacuum fluctuations so that they do what we want, prevent the mirror's quantum shaking from hiding gravitational waves. And Caves figured out the precise manipulations to do that. Squeeze the vacuum fluctuations, reduce one aspect of them while increasing another in precisely the right way, a different way at different frequencies. In 1983, Jeff Kimball invented a powerful technology for squeezing the vacuum. In technical language, send the vacuum fluctuations through a carefully tuned laser-pumped nonlinear crystal, and then through a long filter cavity. Next came a 36-year struggle to build and perfect Kimball's squeezer, make it strong, accurate, and robust. Kimball at Caltech worked the problem for a decade, and then LIGO research groups took over at MIT and in Germany and Australia. And finally, in 2019, a simple form of squeezing was mature enough to be implemented into LIGO. Almost miraculously, this brought a 50% increase in detections of colliding black holes, signals that had been hidden by the mirror's exceedingly small quantum shaking. Seeing LIGO's success, private companies then embarked in 2019 on implementing squeezed vacuum technology into their own technologies. Xanadu for photonic quantum computing, and with DARPA impetus, miniaturized squeezers to use in gyroscopes and magnetometers for navigation. In the meantime, in 2023, LIGO implemented a more powerful variant of squeezing, bringing us to several black hole collisions each week. This history of squeezed vacuum technology is similar to that of some other radical new technologies. Foundations and then gestation in American universities, often with international stimuli. The technology, with risk of failure, is brought toward maturity for 10 or 20 years or more in universities with government funding, and then private companies then and only then see the possibility of profit at acceptable risk and begin investing heavily. The Trump administration's attacks on American universities are endangering this route for new technologies. Alternative routes are needed, preferably routes with strong international collaboration, so that no nation can gain an advantage by single-handedly bringing a powerful, disruptive new technology to maturity. Thank you.